Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Okay, we may discuss on two type of analysis. Okay, for the first one is by using the chart, and another one is using the what we call the method of slices. Okay, so we discuss first on the use of the chart. Okay, so and then I also may discuss on how they develop this kind of chart, okay, by using what we call as a dimensional analysis. Okay, if I'm not mistaken, I have shared this lecture on dimensional analysis for the research methodology class. Okay, however, because of this class, it, there are several students undergraduate. Okay, is not join the research methodology class. So in that case, to explain again, okay, on the dimensional analysis. Okay. So actually, the chart is used to obtain what we call as a preliminary factor safety value. Okay. So we have several type of chart here. Okay. We have Taylor stability number. Then we have Jumbo stability chart. Okay. Then we have Bishop and Morgenstern chart for effective stress analysis. Okay. And then we have a Morgenstern graph for rapid drawdown. Okay. However, we only may discuss on the use of the Taylor stability chart only. Okay. So this is an example of the Taylor stability number chart. Okay. Where we consider this the type of the slope, okay, where it have a beta height of the slope and also the height of the slope to the what we call as to height strata. Okay, so from there we may determine what we call as the stability number. Okay, so from this stability number, at the end we may obtain or we may determine the factor safety value. Okay. So when we look on this chart, okay, so we can identify that this chart is dimensionless. Okay. For example, if beta doesn't have any units, okay, so it is only angle value. Okay. So then we also have a phi or phi, okay, where the phi or phi is also using the degree value. Okay. Then we have another stability number. Okay. So for this stability number, the gamma times h. Okay. So when the gamma times h, the value is equal to kilonewton per meter square. Okay. Then we have divide with c. Okay. So when kilonewton per meter square divide with kilonewton per meter square, so this stability number will become dimensionless. Okay. So that is the stability number. Okay. While we have here ND. Okay. So ND is also a ratio, okay, between the height from the top to the height layer over the height of the slope. Okay. So how they derive or develop this kind of dimensionless chart? Okay, so we discuss a little bit by referring to dimensionless analysis. Okay, so perhaps, okay, if you have heard or learned on this dimensional analysis during my research methodology class, so you can recap or refresh again. Okay, while for the undergraduate student, okay, it will be new for you. Okay, actually, in hydraulic, if I'm not mistaken, you have learned, okay, on this dimensional analysis. Okay. So before we move to several examples, okay, I will discuss it. Dimensional analysis. So this is one method of slices. Okay. So this analysis where some of the researcher or reference book they call as Buckingham 5 theorems. Okay. So we look on the introduction part. Okay. So dimensional analysis is a method to deduce elements of the form of a theoretical relationship from considerations of the variable and parameter they make up that relationship. Okay. So actually it is based from theoretical relationship. Okay. So we want to identify how many elements that govern what we call as the output. Okay, means that from the input and the output, okay, how many elements that contain, okay, to any particular problems. Okay, so in that case, okay, the elements we call as a variable or parameter. Okay, so in this dimensional analysis, okay, so we may discuss, we may need to consider the input and also the output. Okay, I will show some of example later on. Okay, so dimensional analysis of a problem that lead to a reduction in number of variables that must be studied in order to understand the problems. Okay, so for example, due to time constraint, okay, so we could not investigate or cover all the parameter or the variable that may affected the output of the study. Okay, so in that case, we can reduce the number of the variable in our study. Okay, and just focus on the important or the most influence factor. Okay, and also we may identify which parameter has not been uh, studied by previous researcher before. Okay, so that's the idea. Okay, so the key is to create dimensionally homogeneous equation whose form does not depend on the unit of measurement. Okay. For example, the stability number. Okay, so when we divide the unit weight times what we call as meter, okay, over CU. So at the end, the stability number doesn't have any units or it doesn't have any units. Okay. So governing equation cannot just be plucked from the air. They must come from an underlying insight into the phenomenon that is being modeled. Okay. So we need to refer to any reference or any theoretical part, okay, because we want to make use all of the parameter, okay, that has been listed in based on the theoretical part, okay, to be included in this dimensional analysis approach. Okay, so the theory of dimensional analysis is encapsulated in Buckingham theorems. Okay, so Buckingham 5 theorems state that if there are n variable, okay, in a problem and this variable contain m primary dimension, okay, so we have here MLT or MLT is mass, length, time. And then we have another one which is FLT, force, length, time. Okay, so the equation relating all the variable must have n minus m dimensionless group. So we need to count how many n variable include what we call as the output and also the input. Okay. So once we have count, okay, the next task is to determine what is the number of the primary dimension. Okay. So let's say if we are using MLT, okay, so for every variable, so we need to determine how many primary dimensions uh, included in each variable. Okay. We may discuss later on to see to 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 show in an example. Okay. So Buckingham refer to this group as phi group. Okay. So that's why they call as Buckingham phi theorems. Okay. This one. Okay. Where the phi. Okay. So we list all together all the important input and output. Okay. So the phi group must be independent of each other, and no one group should be formed by multiplying together power of other groups. Okay. So for each dimensional less equation, okay, should be formed, okay, and we need to make sure that we use all the variable that we have derived, okay, and also make sure that we not repeat we not repeated use the same variable, okay, unless if we could not uh, construct for the next dimensionless equation. Okay, I will discuss later on. Okay. So the method offer the advantage of being more simple than the method of solving simultaneous equation for obtaining the value of the indice. Okay, so this method is much more easy compared to any other methods, okay, in providing this kind of dimensionless equation. Okay, so in this method of solving the equation, there are two conditions. Okay, so we need to obey or follow this condition. Okay, the first one, each of the fundamental dimension must appear in at least one of the m variable. Okay, so that is the first rule. And the second one, it must not be possible to form a dimensionless group from one of the variables within a recurring set. A recurring set is a group of variables from a dimensionless group. So we cannot repeat again, okay, unless if as I told you previously, unless if it is very important for us to reuse or to use any parameter to create for the next dimensionless equation. Okay. So fundamental quantity must commonly employ are based on Newton's second law, which state that the rate of change in momentum of a body is proportional to the applied force. Okay, as a simple terms, so for the second Newton law, F is equal to m times a, which is force equal to mass times accelerations. Okay. So making unity out of the constant value, so the F is the F itself, okay, while mass is the mass, okay, and then we have acceleration there. Okay, for the acceleration is kilonewton per second, per kilometer per second square. Okay. Sorry, meter per second square. Okay, because that is L. Okay, so this L, okay, T, okay, is considered as a kinematic. Geometry, and T is the kinematic, while F and L we consider as dynamic. Okay, so in that sense, F either we use FLT or MLT because F and L is considered as the same dynamic value. Okay. So the equation relates 4 dimension. Okay, this is for the primary dimension based on the Newton's second law. Okay, where we have F, M, L, and T. Okay. Therefore, while L and T is the fundamental dimension required for geometry and kinematic, the third fundamental dimension is dynamic, can be either force or mass. Okay. So we need to choose, okay, based on which group of primary dimension to be used for our analysis later on. Okay. So the choice of this quantity depends upon the measuring system, whether to employ the MLT system SI methods or the FLT system, which is the British system. Okay. So, however, in this work, since mass is the fundamental physical property, the latter are employed in deriving dimensionless value of the equations. Okay. So in that case, this researcher used the FLT rather than use the MLT. Okay. So selection of the relevant independent parameter can be quite difficult. The resolution of relay problems requires sufficient experience. It is very important, okay, for this kind of approach to be used, okay, when we want to carry out for small scale modeling, okay, because when we use a certain type of geometry, or for example any testing chamber, okay, so we need to use the dimensionless equation approach in order to allow for any other researcher to validate or to reuse our result, okay, if they conduct any physical modeling test, okay, which is not have a same geometry with the one that we have carried out. Okay. So dimensional analysis associated with Buckingham-Phi theorems provide useful hint in determining the various factors that involved in the analysis and relevant data to be collected. Okay. So, okay. So that is the sum of explanations on the Buckingham-Phi theorems. Okay. I guess it's very difficult to understand unless, okay, we see for several examples, okay, and then we can easily understand, okay, how to use this Buckingham-Phi theorem approach. Okay, so slope, for example, this is slope in cohesive soil. Okay, so if we are referring to cohesive soil, okay, so definitely there will be no phi value. Okay, so in that case, we need to eliminate the phi value in our input parameter. Okay, so we need to count how many input parameter and also include the output parameter in our calculation or in our determination of the n number. Okay, so here we have Cu. Cu is the underlying shear strength. Okay, so then we have a gamma here. Okay, from the gamma we have the theta. Okay, so from theta is the gradient of the slope. Okay, so from the theta we have a height of the slope. Okay, and then we have a thickness of the slope from the toe to the height strata. Okay, so that is for the input. Okay, why for the output? Okay, so usually, okay, for any slope stability analysis, okay, we may determine the factor safety value. Okay, so this factor safety value is considered as a part of n number. Okay, so then after we list all the parameter here, so we need to count how many n value for this example. So we have fs here one, which is factor safety, is the output. Okay, so the rest is the input. Okay, so then we have 2 h theta 3 cu 4 gamma 5 delta 6. Okay, so we have 6 what we call it as n value. Okay, so for every n value, okay, we need to determine the value for the primary dimension. Okay, so basically for the fs, okay, because fs is a ratio between driving force or driving stress with resisting force or resisting stress over driving force or driving stress. So definitely fs is equal to 1 because it doesn't have any what we call as units. Okay, so it is not considered as a primary dimensions. Okay, so that's why f is equal to 1. Okay, so then we have here h. Okay, so h is considered as a geometry. Okay, so the l, they only have l here. Okay, so theta is related to degree. Okay, so it doesn't have any units, so we also consider as a 1. And then we have a cu. Okay, for the cu is the under shear strength. For the under shear strength, F is the force, which is the kilonewton. Okay, L power by -2 is meter square. Okay, so in that case, we have 2 primary dimension here. Okay, and the second last is the unit weight. Okay, so then for the unit weight, we have F times L power by -3. Okay, which is the unit weight equal to kilonewton per meter cube. Okay, and the last one is the D. Okay, so the D is the geometry, which is equal to L. Okay, so in total, the value for the primary dimension, okay, first we have L, so we count as a 1. Okay, 1 we not consider as a primary dimension. Okay, then we have F here. Okay, F is also considered as a primary dimension, so we have another 1, 2. Okay, so L power by -2 is already been count. Okay, previously from the H. Okay, then we also have F here. So F is already count, which is represent the CU. L power by -3. Okay, also has been count. Okay, which is the L power by -3. Okay, which is L is the geometry, while F is the dynamic. Okay, so the last one is the L. L is also has been considered. So at the end, we only have 2 primary dimension. Okay, so means that for primary dimension, it can be it can has 3. Okay, or I guess minimum 2. Okay, so 6 minus with 2 is equal to 4. Okay, so in that case, we need to propose for the primary dimension. Okay, so we need to have at least, we need to have 4 primary, we need to have 4 dimensional equation. Okay, so to make it easy, okay, first we consider the value which is represented as a 1. So because it is already dimensionless. Okay, so F here. Okay, and then we have another F, which is theta. Okay, then we have another equation, Cu over gamma H. Okay, so Cu over gamma H. Okay, so we can consider as another dimensionless equation. Okay, then from there we need to generate for another equation. Okay, because we already have used H. Okay, and our intention is to look on the stability number based on the H of the slope. So we come up with another D over H. Okay, for the last equation. Okay, so actually it depends on what we call as the research interest. Okay, for example, if you want to derive or want to establish any equation based on length, okay, uh, uh, at the second portion of the equation, okay, so you may consider that as the your most important equation or units that you want to use to derive for equation. Okay, so for this case, most probably the author, okay, want to look on the effect of the H towards the stability of the slope. Okay, so from this dimensionless equation, okay, so they come up with the what we call as Taylor design chart. Okay, so slightly different with the one that I have showed previously. Okay, however, the idea is here we want to determine the stability of the. We want to determine. We want to produce. Okay, we want to produce. What we call as a dimensionless chart. Okay, so D over H doesn't have any units. Theta also doesn't have any units, while stability number also doesn't have any units. Okay. So later on, I will discuss on how to use this chart in order to gain the stability of the slope. Okay. So that is the idea, how Taylor developed this kind of methods. Okay. So it means that, for example, if somebody have carry out testing, okay, under a different testing chamber or testing box, okay, so he can use this stability dimensionless equation, okay, because it is a dimensionless, so it doesn't relate to any what we call as any certain or any range of dimension. For example, if you want to test on 200 millimeter times 400 millimeter testing chamber, okay, so if we come up with the dimensionless equation, so most probably any researcher that have used a different size of box can also use this dimensionless equation. Okay, so that is how they derive this dimensionless equation. Okay, from the Buckingham Phi theorems. Okay. So the second is the four-cone method. Okay, so this four-cone method used as a quick measure of undrained strength in the laboratory. Okay. So normally we use this approach to determine the liquid limit of cohesive material. Okay, so what is the important parameter here? Okay, the first is the alpha, okay, which is the angle of the cone. Okay, for example, when we use when we want to determine the liquid limit, okay, so we use we use the alpha of 60, okay, for the four cone methods. Okay, so M is the mass, then we may convert to what we call as weight. Okay? So that's why they have W here. Okay? So Cu is what we call as the undrained shear strength of the soil. Okay? And D is the what we call as uh, the depth of penetration depth. Okay? So once we have identified all the important parameters, so we list here, we have D, W, CU, and alpha. So in total, it has four variable or parameter. Okay. So then the next step is for each variable, we may determine the primary dimension. Okay. So we obtain 2. Okay. So 4 minus 2 is equal to 2. Okay. To make it easy, alpha should be used first and the rest should be put in one equation. Okay. So that is the for the four cone methods. Okay. Actually, I'm using this equation, okay, to for my master project study, okay, where we want to determine the plastic limit value, okay, by using a four cone method rather than we use the thread rolling method or Casagrande methods. Okay. So this formula has been used or has been developed properly by Wood and Rowe from Oxford University. Okay. So the next is the relationship ultimate load on a footing. Okay, so this is based on the bearing capacity value. Okay, where we have here PU is the output, which is the load, ultimate load. Okay, and then we have L, which is the length of the soil. D is the depth of the soil. B is equal to width of the footing. Then we have C, phi, and gamma, because it doesn't mention type of soil in the question. Okay. So then we assume it is a normal type of soil where it has C and phi. Okay. So then all together we have 7 n value. Okay. So for every n value, for every parameter, okay, we need to get the primary dimension. Okay, so for this case, the primary dimension is equal to 2. So then 7 minus with 2, then we need to list all the important what we call as dimensionless equation. Okay, in all 5 uh, dimensionless equations. Okay, so for example, the easy is to use whatever that already dimensionless. For example, phi. Okay, so the rest it may depends on your what we call as your research interest. Okay, so if you want to study on B, okay, to look on the B effect, so most of your study should include or it should include the B, okay, in deriving the dimensionless equation. Okay. So the last one is the vertical cut. Okay, we want to investigate what is the input and also the output. Okay. So the output is the factor safety, okay, as we have discussed previously. Okay, then we have the input, which is alpha, gamma, Cu, and also H. Okay, so from all these important parameter, then later on we determine the stability, the primary dimension. So 5 minus with 2, so then we need to create at least 3, we need to create 3 dimensionless equation. So we have 1 Fs alpha second, and the rest is to use all the variable to form uh, one equations for the dimensionless. Okay, that is for the vertical cuts. Okay, so that is the idea how Taylor come up with this kind of approach. Okay, where he uh, want to use any different type of testing. Okay, to be validated from his uh, Taylor design chart. Okay. Okay. So now I move to an example, okay, on how to make use or to determine the flight safety from the chart. Okay. Now we stop first. Okay, Taylor chart. Okay. Okay, this is based on Dr. Kamarudin example. Okay. I will upload in the what we call it in the e-learning later on. Okay. So a dimensionless parameter NS, okay, obtained by correlating the unit weight and the cohesion of the soil and the height of the slope, okay, is plotted as the function of the slope angle beta, the various value of internal friction angle of soil. Okay. So for a slope soil with phi equal to 0 and beta less than 53, the failure surface is deep below the crest of the slope and must be hello.
Doktor tak share slide.
Oh, sorry.
Ha.
Terima kasih. Okay. Sorry Okay. So okay, for stability analysis of finite slope using Taylor chart. Okay. So this example is obtained from Dr. Kamarudin reference book. Okay. So we look on this example and then we move from to another example from Dr. Noli Gofar. Okay. A dimensionless parameter obtained by correlating the unit weight, okay, unit weight and cohesion of soil and height of the slope is plot. Wait a minute. Okay. So and plot as a function of slope angle beta for various value of internal friction angle of the soil. Okay, later on we may look on this on the chart. Okay, for a slope of a soil with phi 0 and beta less than 53, okay, the failure surface is deep below the crest of the slope and must be correlate to the depth of the slope to the underlying hard stratum. Okay, for C and phi soil, trial and error procedure are as follow need to be undertaken to analyze the slope stability. Okay, so this is the procedure. Okay, when we want to use this Taylor chart. Okay, based on Dr. Kamarudin's book. Okay. So first, in terms of internal friction angle of soil, which is the Fs. Okay. So then determine the mobilized internal friction angle, which is the phi r, where phi r is equal to tangent times tangent phi over Fs phi. Okay. So from there, okay, after we obtain the phi r, then we need to look on the Taylor chart, okay, which is I already put in this example, okay. So this is the example of the Taylor chart, okay, for the case of C and phi, which is soil have C and phi value, okay. 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 And obtain the NS. NS is stability number. Okay. So then determine the mobilized coefficient, which is the CR, where NS is equal to gamma times H over CR. Okay. So once we already obtain the stability number, then we may identify what is the CR value. Okay. So calculate the factor safety C, where C over CR is the factor safety of C value. Okay. So the next task is to uh, 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 we have discussed previously, okay, that we want to differentiate between the non-linear and a linear relationship. Okay, that's why we need to make up to three analysis or three calculation. Okay, so this is an example. Okay, using the Taylor chart, appendix C1, determine the factor safety of the slope shown in figure 1. Okay, if boleh dengar tak? Can you hear me? Hello?
Yeah.
Boleh?
Not
Yes,
clear,
Prof.
actually,
I
bro.
hear you, but not clear.
Yeah,
Just
there are a lot cutting in voice.
Okay, sorry. Okay. So now is it clear now?
yes, it's now clear.
Okay. Okay, sorry. Okay.
Oh.
Okay. So determine the fire safety of the slope shown in figure 1. Okay, phi is equal to 0 and phi is equal to 20. Okay, so we have two value of phi for this example. Okay, so the height of the slope is 8. Okay, the degree is 60. So we have here 17 for the unit weight and C is equal to 22. Okay, so now we need to determine the factor safety, okay, when the phi is equal to 0. Okay, so this is the C by using the chart. Okay, so we need we need to determine the stability number later on. Okay, so the first procedure, okay, by assuming Fs phi is equal to 1, okay, then we determine the phi r is equal to the tangent phi over Fs phi. Okay, so we already put Fs phi here equal to 1. Okay, so then if phi is equal to 0, so tangent 0 over 1, it will become 0. Okay. Okay. For example, if we increase the factor safety to 2, okay, it still become 0. Okay, so for this case, it is wise only to carry out for one analysis only, because the rest, the value also will become 0. Okay, although we increase the factor safety here. For example, 3, tangent 0 over 3 is also 0. Okay. Okay. So based on Taylor chart, okay, it can be observed that stability number is equal to 0.19. Okay. So how to use the chart? Okay. So based on this chart, okay. So first, the slope value, what is the slope value, is equal to 60. Okay. So that is the slope value. So 60 here, then using a ruler, okay, so then move upward until it meets the phi r equal to 0. Okay. So for our case, the phi r is equal to 0. Okay. So from there, we can obtain, okay. So this is 60 here. So approximately the value is 0 0.2 something. 0. Okay, 0.19. Okay, 0.19. Okay, so that is the value for the stability number. Okay. Okay. So this is the 60. Okay, and then the 60 should bring the 60, okay, until it meet the what we call the line of 0. Okay, so actually it is around 0.2 something, 0.20 0.20 2. Okay, or 0.205. Okay, so okay, so it can be 0.205. Okay, so slightly above 0.19. Okay, so then from this stability number, okay, we should determine what is the CR. Okay, rearrange the stability number, because in here the stability number is equal to CR over gamma H. Okay, so when we rearrange there, so CR will be on the left, the rest will be on the right. So 0.19 multiply with unit weight of soil 17 multiply with 8 is the height of the slope. So we obtain 25.84. Okay. So once we already obtained the CR, okay, so C over CR is equal 0.85. Okay. Theoretically, the slope fail as the factor safety is less than 1. Okay. Because although we increase the phi value, the factor safety value, so the phi R become 0 as well. Okay. So that's why we doesn't require to carry out for the second and third attempt. So at the end, the factor safety is less than 1. Okay. So now we look for the second example, okay, where the phi is equal to 20. Okay. So tangent 20 over 1, so the phi is equal to 20. Okay. So then for the phi r, okay, when we look on this graph, okay, the same procedure, okay, until it meet the 20, okay. So from this, we may determine the stability number. Okay. For this case, the stability number is around 0.10 something. Okay. Okay. However, for this case, 0.1. Okay, 0.10 something, so 0.095. Okay. So when we use 0.095, okay, then we multiply with 17 and then multiply with 8. So then we obtain the stability, the CR is equal to 12.92. Okay. So then calculate for the FSC, okay, where C over CR, so we obtain factor safety is equal to 1.7. Okay. So FSC is equal to 1 and it's not same with the FSC. Okay, so we need to carry out or repeat for at least 2 attempts more. Okay, so for this case, Dr. Kamaruddin, okay, increase the factor safety to 1.5 and then he obtained 1.35. Okay, then he increased 2.0 and then he obtained 1.22. Okay, then plot the relationship and get the line of equality. So the factor safety is equal to 1.4. Okay, so that is for example for the Taylor chart. Okay, I will try to look on yeah, might be this chart is a little bit different because it's not provide the same stability number with the answer from the solutions. Okay. Okay, so that is for the stability factor safety, okay, for using the Taylor chart. Okay, so now we look on Dr. Noli example. Okay, so okay, you can read the content later on. Okay. Okay. So okay, so this example by using the chart. Okay, a cutting in a cohesive soil form a slope angle of 35 and the height of 8. Okay. The undrained cohesion is 40 and the unit weight is 18. Using Taylor chart, Taylor stability chart determine the factor safety of safety against shear failure for a hard stratum exists below the slope and the hard stratum exists 4 meter below the slope, below the toe. Okay, so this is another way, okay, by referring different stability or different what we call as Taylor design chart. Okay, so a little bit different with this one. Okay. 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 However, the intention is same. Okay. So most probably there are several design chart is being proposed by Taylor. Okay. The first from Dr. Kamarudin. Okay, we may use the procedure where we identify the FSC, SFE, and then get the FSC. Okay. But for this case, it is a straightforward. Okay. Okay. By using this Taylor design chart, okay, a hard stratum exists well below the slope. Okay, so that is the condition. Okay. And over the. Okay, we look first on the solution. Okay. So Cu is equal to 40, unit weight is equal to 18. Okay. So because the hard stratum exists well below the slope, so they consider Nd is equal to infinity. Okay. So then the phi is equal to 0 and then the beta is equal to 35. Okay. So first we need to identify what is the stability value, the NS. Okay. So the hard stratum exists at the exists on the toe. So means that this hard stratum exists here. Okay. So ND doesn't have any value. Okay, because sorry, the ND is infinity because there doesn't mention how the distance of the hard stratum with the slope. Okay? So in that case, they assume it is an infinity. Okay? It's very far from the distance is very far. Okay? So when they assume ND is equal to infinity, okay, so with the slope angle of 35, okay, so 35 here, okay, so 35, okay, so with the ND is equal to infinity, okay, so then definitely the value of ND is the value of the stability number is equal to 5.52, okay. So that is the value for the what we call as for the stability number. Okay. So when we obtain the 5.52, okay, then we rearrange the factor safety value. Okay. Okay, we look on this formula 5.26. Okay. So the factor safety is equal to NS times C over gamma H. Okay. So 5.52 times 40 over 18 times 8 is equal to 1.53. Okay. So that is for the A. Okay. For the B, a hard stratum exists at 4 meter below the toe. Okay. So 4 meter below the toe. Okay. While the height of the slope is 8 meter. Okay. So 8 plus 4 is 12. So from there we can get the ND is equal to 1.5. Okay. So when the ND is equal to 1.5 with the slope of 35. Okay. So with the slope of 35, so we bring a straight line until it meet 1.5. Okay. So then move to the right, okay, to the X y-axis to determine the stability number. Okay, so the stability number is equal to 6. Okay, is around here 6, okay, which is 1.5. Okay, this is 1.5. Okay, so it meets the 6 for the stability number. Okay. So 6 times 4, 40 over 18 times 8, the factor safety is equal to 1.65. Okay, a little bit higher compared to the first example. Okay, so that is for the first example. Okay. So determine the factor safety in terms of effective strength for the slope with beta is equal to 40 and the height 10. The property of the R as follow: 20, 5, 10, gamma 17. Okay. The degree of the slope is 40. Okay. So 40 here. Okay. So it doesn't mention the ND value. Okay. So the phi is equal to 10. Okay. So we move until it meet 10. Okay. Then we obtain the stability number around 10 something. Okay, 10.7. Okay. So then the factor safety is equal to 1.26. Okay. Okay. The last is the factor safety with the height of 5.5 and the angle of 40. Okay, the unit weight of the soil forming of the slope is 60.5, while the shear strength parameter of the soil is C and phi is equal to 10. Okay. So when the beta is 40, phi is equal to 10, h is equal to 5.5, unit weight is equal to 16.5. Okay. The factor safety, okay. Okay, factor safety equal to 1. Okay. Where from the NS chart 10.7, okay, then using C is equal to 20. So then we obtain the factor safety of C equal to 2.36. Okay, this is similar with Dr. Kamarudin example. Okay, then when the factor safety is equal to 1.8, okay, then we repeat the same procedure. Then we obtain the factor safety of 1.83. Okay, then later on they consider 1.8 and 1.83 is similar. Okay, so the result is 1.8. Okay. Okay. So the last one, determine the safety factor for a submerged field with a height of 30 meter and slope angle 30. The saturated unit weight of the soil is 19, while the shear strength parameter of the soil C 35 and phi 5. Okay. So solution using the factor safety is equal to 1. Then from the Taylor chart for phi 5, beta 30, okay, and S is equal to 9.25. Okay, then 9.25 times 35 divide with unit weight. Okay, effective unit weight 19 minus 9.8 times 30. So the factor safety of C is equal 1.17. So in that case, they consider factor safety of C and factor safety of P is equal. So they conclude the value is equal to 1. Okay. Okay. So that is for the Taylor design chart. Okay. We may continue, okay, for the method of slices after we have a break, okay, for 10 minutes. Okay.